Good day, I'm Norman Wildberger. In this series on foundational issues in mathematics, we've been talking about algebra. Algebra is a large subject characterized by the use of letters to often represent numbers. And we've talked about the usage of letters in equations as representing unknown numbers. Today we're going to look at a different role for letters in algebra by first of all having a look at some interesting patterns formed from geometrical sequences. Here are the squares. These are actually literally geometrical squares, and we're counting the areas of these squares. 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, and so on. These numbers are important numbers in mathematics. They're called the squares. And we can represent them algebraically by the use of the term n squared. So the nth square is n squared, which I remind you means n times n. Here the letter n is representing a natural number. In other words, 1, 2, 3, 4, and so on. Here's another famous family of special numbers, the triangular numbers. Let's give them a name. Let's call the nth triangular number t sub n. And geometrically, how they arise is by stacking up some balls in a triangular kind of pyramid. There's 1 ball, there's 3, there's 6, there's 10, there's 15, and we can continue. At each stage, what we're doing to go from here to here, say, is we're adding an extra row of balls at the bottom. So that T3 there is reproduced here, and then we add 4 more balls to get T4. Similarly, the T4 is reproduced here, and we're adding 5 new balls to get T5. And here are the triangular numbers, 1, 3, 6, 10, and 15, and so on. It's a little bit less obvious now what a general formula for the nth triangular number is, and that's what we want. Something just like this, but telling us what exactly the Tn is in terms of n. Triangular numbers have been studied since antiquity, and they have lots of interesting properties. Here's a way of analyzing patterns of numbers in a more general way, which applies also to other interesting sequences or patterns. We write down the sequence, starting, say, with 1, 3, 6, 10. These are our triangular numbers. And then above any two of them, we write what the difference is. Difference between 3 and 1 is 2. Difference between 6 and 3 is 3, and so on. Or to put it another way, we write how much we have to add to this one to get to the next one. And we've seen already that these differences increase linearly. They go through all the natural numbers. That's made a little bit clearer by actually deciding to start our triangular numbers with 0. Then we have a difference of 1 as well, which makes it aesthetically a little bit more pleasant. So let's do that. We could also examine this sequence, which is just the sequence of all natural numbers in terms of differences. Well, the difference between any two of them is just 1. So there's the line of differences between the natural numbers, and of course the differences between these are all 0, and that's sort of where things stop. What about a formula for the nth triangular number? Well, here's T4, and another way of thinking about what that is it's 1 plus 2 plus 3 plus 4. So there it is there as a sum. Another way of representing this triangle of circles is to represent it more with some boxes. 4, 3, 2, 1. And if we do it that way, then we can play the following trick. So we can take our copy of T4 over here in blue, and then we can take a second copy of it as well in red and invert it and put it on top to match up and to form a rectangle. In this case, a rectangle of sides 4 and 5. That's telling us that 2 times T4 is 4 times 5. And that works in general. 2 times Tn is going to be a rectangle with sides n and n plus 1, so the total area will be n times n plus 1. From which we deduce that Tn is equal to n times n plus 1 over 2. So here's another use of letters in algebra to allow us to write formulas for patterns. The n here is not representing an unknown number so much as a general number. And it's allowing us to express an arithmetical fact that's valid not just for one triangular number, but for any triangular number. In fact, this formula is an important formula because it's directly connected with this kind of arithmetic sequence. So in other words, we can interpret that little computation we made about Tn as a formula for this arithmetic series. 1 plus 2 plus all the way up to plus n, the sum of all the numbers from 1 to n, which is just the number of balls in the nth triangular number, is n times n plus 1 over 2. That's our formula for Tn. This kind of formula is sometimes a little bit ambiguous. And so we mathematicians like to introduce a more precise notation for talking about sums. This is the summation notation represented by this capital Greek letter sigma, sigma for sum. So here's our convention that instead of writing 1 plus 2 plus 3 plus 4 plus 5, we'll simply write the sum from k equals 1 to 5 of k. So this expression right here means this by definition. Here's a more general example. The sum of all the numbers from 1 to n. 1 plus 2 plus 3 plus 4 all the way up to n minus 1 and up to n. That sum is now represented in the summation notation by this sign. The sigma, that stands for sum. This index k is telling us what, first of all, we're summing and what the range of summation is. K is running from 1 to n, and we're summing k. The beauty of this summation notation is that it's quite flexible and allows us to talk about other kinds of sums. For example, 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared could be written more economically as the sum, k equals 1 to 5, of k squared. Here's the general formula that extends this. I'll just give it to you for now. We'll have a look at proof later on. The sum of all the squares from 1 up to n squared, so the sum k equals 1 to n of k squared, is n times n plus 1 times 2n plus 1 divided by 6. So if n happened to be 5, then we would have a 5 here, a 6 here, an 11 here. The 6's would cancel, and we would get 55. This last sum that we looked at, the sum of all the squares, can also be studied in terms of a table of differences. It's also quite interesting. The differences between the squares are all the odd numbers. 3, 5, 7, 9, 11, and so on. Further differences are all 2 and then 0, so that's relatively easy. But we can also extend this table downwards, as long as we have a starting point. So suppose we start with 0. Then this line is going to be the line of the sums of squares. This 55 here represents 1 squared plus 2 squared all the way up to 5 squared. That's the number we already calculated. So here are the sums of squares. That's a more complicated sequence from the sequence of squares obtained by going down in this table of differences. This is just the beginning of talking about patterns of numbers, and next time we're going to look at some more patterns. Give us some more practice in trying to understand geometrical patterns arithmetically and using algebra to encode the results. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.